question about the universe at its smallest scale. We're looking inside atoms, specifically at that. Well, that space that seems to be between where electrons are. You sent us some great material on this. And yeah, it definitely messes with your classical intuition. Forget the tiny planets whizzing around a sun model for a moment. This is quantum mechanics, and it's famously weird. Okay, let's get into it. If that space isn't just empty void between electron paths, what is going on? How do electrons even deal with it?
That really is the heart of the matter, isn't it? It forces you to think completely differently. We have to shift from, definite spots and paths to thinking in terms of probabilities, waves. It's fascinating how different the quantum world is from what we see every day.
Right. So first things first, we got to ditch that old picture, the little balls orbiting.
Absolutely. That's the biggest hurdle. An atomic orbital isn't a path. It's not like a racetrack. It's actually a mathematical function. It comes from the Schrödinger equation, and it describes the electron's wave-like behavior inside the atom.
A mathematical function.
Okay. And the key part for visualizing it is when you square that function. It's written as Michaelis modulus I squared. That gives you something called the probability density.
Probability density, meaning?
Meaning it tells you where you're most likely to find the electron if you were to look for it at any given moment.
Okay. So less orbit, more probability cloud. Is that a fair way to think about it?
That's a great analogy, yeah. An electron cloud. The denser the cloud in a particular spot, the higher the probability of finding the electron right there.
And it's fuzzy, not like a solid shell.
Exactly. These clouds don't really have sharp edges. Technically, the math says the probability extends out infinitely, but it gets incredibly tiny very quickly as you move away from the nucleus. So the shapes you see in textbooks, the spheres, the dumbbells, those are just boundary surfaces. We draw them to capture, say, 90% or 95% of the probability, just to give us something to visualize.
Got it. So the orbital itself is this fuzzy probability zone, but what about the space between these zones? Like, between the one's cloud and the two's cloud, or even within a orbital, between those two lobes, what's in that space?
Well, as you move away from a high probability spot for one electron, its probability naturally drops off. The cloud gets thinner, you could say.
Mm-hmm.
But here's where it gets really quantum and counterintuitive. There are specific places where the probability of finding an electron for one specific orbital drops to exactly zero.
Zero. Like not just really, really small, but actually zero.
That particular electron state, yes, absolutely zero. These places are called nodes.
Wow, okay. Nodes.
And there are different kinds. The sources mention radial nodes. These are like spherical shells at certain distances from the nucleus. So the 2's orbital, for instance, has one radial node. It's a sphere where the probability of finding the 2's electron is zero. It separates an inner bump of probability from the main outer region.
Huh. So there's a shell of nothingness for that electron.
For that electron, yes. The 1's orbital doesn't have any radial nodes. The 3's has two. It depends on the energy level. Then you also have angular nodes. These are different shapes, usual planes or sometimes cones that pass right through the nucleus. P orbitals, those dumbbell shapes. They each have one angular node. It's a plane slicing through the middle, separating the two lobes. For a p orbital, that node is the YZ plane. Zero probability for the pure electron on that plane.
Okay, planes and spheres of zero probability, that leads to a big question, doesn't it? If the probability is zero at a node, how does an electron get from one side to the other, like the 2's electron? How does it get from its inner fuzzy bit to the outer fuzzy bit if it absolutely cannot exist at the node in between? It can't just beam across, can it?
Right, and this is where thinking of it as a little ball traveling completely breaks down. It doesn't jump or pass through in any classical sense. The electron exists as a standing wave. Think about a vibrating guitar string. It has points that don't move at all. Right?
Yeah.
Those are nodes.
Yeah, okay, so still points on the string.
Exactly. The electron's wave function in an orbital is like a 3D version of that standing wave pattern. The nodes are just the regions where the amplitude of that wave is zero.
So the electron is the wave, and the wave has 0 points.
Precisely. It's a quantum thing. When you measure it, you detect it as a particle, here or there. But its underlying nature is this wave function. It can be detected on one side of a node or on the other side, but never at the node itself, because its wave function is zero there. It's pure waves-particle duality in action.
Okay, wow. So the node isn't a wall. It's just part of the pattern. That makes more sense. Sort of. But that's all for, like, one electron in its orbital. Real atoms have loads of electrons, right? How does that complicate things? Does a node for one electron mean that spot is totally empty?
Good question. And no, definitely not empty overall. In atoms with many electrons, it gets way more complex. You've got electrons repelling each other, shielding the nucleus. All that stuff affects the orbital shapes and energies. But here's a really key point from the sources. Orbitals aren't neatly separated. They actually overlap in space. They interpenetrate.
Overlap. How so?
Well, take the 2's orbital again. We said it has that main probability cloud further out, but it also has that small inner lobe, remember?
It's closer to the nucleus.
That inner lobe is actually inside the region where the 1's electron is most likely to be found. The 1's and 2's clouds overlap quite a bit near the nucleus.
Ah, I see.
So think about that radial node for the 2's electron, that spherical shell where the 2's probability is 0. Just because the 2's electron can't be there doesn't mean nothing else can. A1's electron, if the atom has one, has a non-zero probability of being found right at the same location as the 2's node.
Okay, so a node is specific to one electron in one particular state. It's not an empty zone for everybody.
Exactly. The space where one orbital has 0 probability might be a perfectly fine place for an electron in a different orbital to be.
Right. Okay, so let's try and pull this all together. If that space between the main parts of orbitals, or even at the nodes, isn't classical empty vacuum, what is actually there? What's filling it?
Well, it's certainly not empty in the way we normally think of vacuum. That whole volume inside the atom is active. First off, you've got field. The strong electric field from the positive nucleus fills the whole atom, and the electrons themselves create their own electric fields, interacting with each other.
Fields, right. Like invisible influences filling the space.
Yes. And then there's stuff from quantum field theory. Even in what we think of as perfect vacuum, there are these quantum fluctuations, virtual particles popping into and out of existence constantly. That's happening everywhere, including inside the atom.
Virtual particles, too. Okay, so definitely not empty.
Definitely not. So the key takeaway is nodes mean 0 probability for a specific electron in a specific orbital state. But the overall atomic volume is buzzing with electric fields, these quantum fluctuations, and crucially, the probability clouds of other electrons from different orbitals overlapping into that same space. It's a dynamic landscape of probabilities and fields, not empty gaps between solid paths.
Okay, so it's a huge mental shift. Forget planets. Think fuzzy overlapping probability waves.
That's it.
And nodes aren't gaps, the electron jumps. They're just 0 points in that electron's specific wave pattern.
Right.
And the space isn't empty because of fields, quantum fuzziness, and importantly, other electron waves overlapping there.
You've got it. Understanding that space means letting go of a classical picture entirely. It's a quantum landscape.
It really forces you to see the atom not as a tiny machine, but as this dynamic, probabilistic system, which is pretty wild. So here's something to chew on. If an electron exists as this wave, and it can be found on either side of a 0 probability node without ever being at the node, what does that tell us fundamentally about what position or even existence means at that tiny scale? Something to think about. Thanks again for sending in the material that sparked this fascinating deep dive.